All right, welcome back to another video. In this session, we are going to look at two concepts. All right, we are going to look at line integral in a vector field. Then we also look at surface integral in a vector field. Okay, so let's begin with line integral in a vector field. So basically, if we talk about line integral in a vector field, I want you to give your answer at the comment section. What is line integral in a vector field? I'm expecting solutions there. Okay, so I want you to imagine this, okay? A force field in space, okay? So we are taking a force field in space, right? So something like wind, okay? Something like wind that is blowing at each point in three-dimensional space, okay? That is blowing at each point in 3D. Okay, so do you know that if you walk through a certain path along, let's say, that field, okay, along that field, the line integral can tell you how much force field does on you. Do you know that? Now, as you move along that path, the line integral can tell you how much force field does on you. So in all, a line integral in a vector field calculates the cumulative effects, okay? It calculates the cumulative effect of a vector field along a curve, So especially this is very useful in physics when we are talking about work circulation, okay? It is very useful in physics for work circulation and flux. Okay, so now that we have the intuitive understanding of line integral, let's now come to the mathematical definition. All right, so let's say that let's f of x, y, and z, okay, equals these position vectors, right? So let's say p of x, y, and z, or I plus q of x, y, and z, or j, plus r of x, y, and z, or k. Okay, so this is the vector field, okay? So this is the vector field. So this be the vector field. This be the vector field. Now, we are going to let r of t, which is the position vector, okay? So let r of t equals s of t I plus y of t j plus z of t k. Right. That is the smooth curve that is moving along the path. So this be the smooth curve C. Okay, so then we can say that the line integral of the vector field F along the smooth curve C is giving us then the line integral of the vector field F along the smooth curve C is giving us F dot dr equals from a lower limit to an upper limit of f of r of t dot r prime of what t dt. So this is how you calculate your line integral of a vector field along a smooth curve. So this expression right here is trying to compute how much the vector field f is aligned with the direction you are moving. Okay, this right here is trying to compute the vector field f, right, that is aligned with the direction you are moving towards, right? So that is the meaning of this expression. So let me write it here. F dot dr is equal to, from lower limit to upper limit, f of r of t dot r prime of t dt. Okay, so this is what will help you to calculate the line integral of a vector field moving along a smooth curve. Okay, so now let's look at the processes or the steps that are involved in calculating the line integral of a vector field. Okay, so we begin with step 1. Okay, so steps 1. The first thing that we have to do when we want to calculate the line integral of a vector field is to parameterize the paths. Okay, so we have to parameterize the path C, right? Once you parameterize the path, then what you have to do, the parameterization is r of t equals x of t I plus y of t j plus z of t k, right? So this is the parameterization that I'm talking about. Okay, so once you are done with the parameterization, the next thing that you have to do is to compute the rate of change, right? Which is the r prime. So to compute r prime, which is the rate of change, right? And this right here represent the tangent vector to the path, right? The r prime represent the tangent vector to the path. So that is step 2. Step 3, we have to express or evaluate the f of r of t, right? So once we are done computing r prime of t, we have to evaluate f of r of t, right? We have to evaluate f of r of t. Then we substitute the parameterized curve into the vector field. So once we do this step, then the fourth step is to take the dot product, right? So we take the dot product of f of r of t dot r prime of what t. So this is what is very important to me. You have to take the dot product of what f of r of t dot r prime of t. So once you are done with that, then the next thing is what? Integrate over the given parameter. So that is step 5. Step 5. integrate over the given parameter. Right? You integrate over the given parameter, and that is from A to B of f of r of t dot r prime of what? T dt. So this is what you integrate. Right? So that is the steps involved in calculating the line integral of a particular vector field. Step 1, parameterize the path, and that is r of t equals s of t I plus y of t j plus z of t k. Then after that, you compute your r prime of t, which is the rate of change, right? Then you evaluate f of r of t by substituting r of t into what? The f. Then fourth, you take the dot product of what? F of r of t and r prime of what? T. Once you are done with that, you set up your integral and then you integrate over the given parameter. And that is this, right? So let me give you some few minutes to reflect on the steps. I'll be back with a question, detailed one, so that we go through to understand the concepts. All right, so welcome back from the short break. Now, this is the question that we are going to use to understand the concept of line integral of or in a vector field, right? So this is our first question, okay? And this is question number 10 from quiz 2, and I'm using code 1, okay? So this is question number 10. Now, the question says that we should evaluate this line integral f dot dr, where c is parameterized by this, right? For 0 less than or equal to t less than or equal to what? Pi on 2. And we have been given the vector field as si minus what? Zk. Okay, so interesting. We are going to analyze this step by step, okay? So that once we solve one problem, you can use that to be to solve the trial problems, right? So solution. Step 1. Step 1. Can you tell me what to do in step 1? I hope you went through the steps, right? So step 1, we have to compute r prime of what? R prime of t, right? So compute, because we already have the parameterized part, right? So let me write that down. R prime of t, r of t is equal to what? Cos ti plus tj plus sine t. Okay, the question has already given us the parameterized part. So what we need to do is what? Step 2. Compute r prime of what? T. Right, so r prime of t will be equal to derivative of cos is negative sine t I plus derivative of t with respect to t becomes 1, so times j becomes j, plus derivative of sine is cos t k. So now we have the derivative of what? R prime of r of t, which is what? R prime of what? T. So the next thing we have to do is to express f of x, y, and z along what? The curve. So within this, we express f of x, y, and z along the curve, right? So that is where we will go and then write f of r of t in the angle bracket form, right? So from here, from r of t equals, this is the same as cos ti, comma t, comma sin t. Here, we know that we can put in f, right? So, and f from the question is, f is equal to xi minus what? Zk. Right, so we are just going to substitute the components into what? F. And we know that s from here is, so let's say that f of xy z is equal to x of t is equal to f of s of t, comma y of t, comma z of what? T. Right, so we are going to substitute what we see here into what? F. So we know that x is equal to what? Cos t, and y is equal to what? T d. Z is equal to what? Sin t k. Okay, so what we have to do is to just substitute into what? F, right? So we are going to have that to be f of x, y, and z to be equal to cos ti minus sin t k. Interesting, right? So the next thing we have to do, which is step 3, is to find f of r of t dot r prime of what? T. So f of r of t dot r prime of what? T. And that will be equal to this dot r prime of t, which is here. Right? So cos ti minus sin t k dot r prime of t is negative sin t I plus j plus cos t k. Right, so we're going to have this times this becomes negative sin t cos t, and then there is no j here, so when you multiply 0 by what? J, you're going to have 0, so the j component goes away. Then we have minus sin t times sin cos t becomes negative sin t cos t, right? So we can see that this and this are the same. So we say that we have negative negative 2 sin t cos t. So this is our dot product, right? So that is step 3. Now step 4, what do we have to do? We just have to set up our integral, right? So we set up our integral. Okay, so I can clean this, okay? So step 4, we set up our integral, right? And then we can evaluate, okay? So we set up the integral from 0 to 2, from 0 to pi on 2 of the dot product, which is negative 2 sin t cos t, or dt. So now the work has become easy, right? The only thing we have to do is to look for identity to replace what? Sin t cos t. So let's factor the negative 2 out. 0 to 2, 0 to pi on 2 sine t cos t dt. Now remember that there is an identity that says that sine 2t is equal to 2 sine t cos t, right? So that is an identity that we have to use to be able to handle this particular problem. Okay, so from here, record that sine 2t is equal to 2 cos t sine t, right? So we need this, right? So we say that cos t sine t is equal to sine 2t over 2, right? So we are going to substitute this in place of this here. So interesting, right? So we're going to say that minus 2 out from 0 to pi on 2 of sine 2t over 2 or dt, right? So now we can easily integrate this. So we have negative 2 times, this is half, right? So we bring it out from 0 to pi on 2 sine 2t dt, right? So this cancels this, and then we have negative 1 from 0 to pi on 2 sine 2t dt, right? So we're going to say that we have negative 0 to pi on 2 sine 2t dt. Now, integral of sine 2t is negative cos 2t over 2, right? From 0 to pi on 2, right? So here we factor the half out, right? So we have negative, negative, positive. So we have half into cos 2t from 0 to pi on 2, right? And this right here, we know that half into cos 2 times pi on 2 minus cos 2 into what? 0, right? So we have half into this takes this, so we have cos pi minus cos 0. Interesting and so amazing. And so we know that this is cos pi, and cos pi is negative 1. So we are going to have half into negative 1 minus cos 0 is as well positive 1. So we have positive 1, then we have half into negative 2, right? And this is equal to negative 2 over 2, which is equal to negative 1. Okay, so this becomes our answer for the question. And please, this is code 1, question number 10. So the answer to that particular question is negative 1. So amazing, right? So please, it's about going through the process and understanding the steps. Once you understand the steps, you can do it with ease. Okay, so that is the answer to this particular question. Now let's take a very short break and then come back for question number 2. Okay, so I'll be right back. So welcome back from the short break. I believe you have been able to go through the first question, the solution of the first question, and you've really understood it. Now, we are back with another question, question number 2, right here. But on the quiz paper is question number 13, code 1. So let's walk through this problem, okay? So this is that if an inverse force field F is given by f of x, y, z equals rho over r, magnitude of r cube, right, dot r, where p is a constant, we want to find the work done by F as its point of application moves along the line segment r equals 2 plus t I for 0 less than or equal to what? T less than or equal to what? 1. So let's analyze this particular problem. This problem is kind of application. Okay, so it says that the force field, right, F, the force field F of x, y, and z is equal to rho over magnitude of r cube dot r, right? And p is a constant. The rho is just a constant, right? And we want to find the work done by F as its point of application moves along the line segment r equals what? 2 plus ti. So we know that r is equal to x, y, z, right? That is what it is, okay? R is equal to what? X, y, z. That is the parameterized part. Okay. So once we know the parameterized part is equal to this, okay, then we know that P and P is what? And P is a constant. Okay, and P is a constant. So we know that our R of T is equal to 2 plus T, comma 0, comma 0. Right. Okay, so once we know this, then the next thing we have to do is that we have to, find the particle. We have to know where the particle moves along the x-axis, right? So the particle moves along the x-axis from x equals 2 to s equals what? 3. The reason is, you see, we have 2 plus t, right? So if t happens to be 0, then x will be what? 2. And if t happens to be what? 1, then we have what? 2 plus 1, which is what? 3. So the particle moves along the x-axis from what? X equals 2 to s equals what? 3. Okay, because I'm doing that from here. You know, the range was given as 0 and 1 inclusive. So if t happens to be 0, then it means that s is moving from 2. And then if t happens to be 1, then it means that s is moving to what? 3. So once we know that, then what we have to do is to just, we have to write our vector field. So step 2. So all this one is what? Step 1. Okay, so step 2, we have to write our vector field out of this information. So we also know that our r is equal to what? X, y, z. Okay, so the magnitude of that will be equal to what? Square root of x squared plus y squared plus what? Z squared, right? Now, we know the magnitude of what? R. So the next thing we have to do is, we were given that R is equal to 2 plus T or I. So we can do that substitution over there. Okay, so we're going to have f of x, y, z to be equal to the rule, which is p all over r, which is x, y, z, right? To the power 3 on 2. We have changed this cube to what? 3. 3 on 2, because the square root itself is what? Half, right? So if you have half times what? 3, you get what? 3 on 2. That is what we have here, times x, y, z. Okay, now we're going to have this to be equal to rule over. Now we know that x, y, z is 2 plus t, right? So we're going to have, okay, so you just write this again and let's do this. Let's do this. We know that this is equal to what? X, y, z, and that is equal to what? 2 plus t, right? So this is basically equal to 2 plus what? T, magnitude of that, and it is the same as 2 plus what? T. So we can substitute this information here, right? So we're going to have that rho over 2 plus t to the power 3 on 2 times. Now this is 2 plus t, right? Now let's try to write this in the position vector form, right? So when we do that, then we're going to have rho over 2 plus t to the power 3 on 2 times 2 plus t, comma 0, comma 0 over here. So we're going to have rho over 2 plus t to the power 3 on 2 dots 2 plus t, right? And we know that this is what? 1, 1, comma 0, comma 0, right? So from here, we're going to say that our work done, the first field is equal to what? Rho over 2 plus t to the power 3 times 2 plus t, right? And that is equal to, that is the dot product, right? We are taking the dot product. So we're going to have rho over 2 plus t to the power 2. Now this is the dot product, right? So now we can integrate over the given interval. So from 0 to 1 of rho over what? 2 plus t to the power 2, right? dt. Okay, so this we can change the format, or we can say that u should be equal to what? 2 plus t. So let's u equals what? 2 plus t. So we have du to be equal to what? dt. Now, I love to do change of limits. So let's say that if t is what? 0, then means that u will be what? 2. And if t is 1, then we have u to be what? 3. Right, so we're going to have from 0. Now we have changed the limit, so it's going to be 2 to 3, 2 to 3 of 1 over u squared du. So beautiful, right? So I love to do change of limit a lot, but the change of limit, when you are doing it, you have to be very careful. When you change your limit, make sure that you put it there. Okay, so we're going to have from 2 to 3 u to the power -2. Remember that there is a p over there, right? The rule times the u. So we have rho into the integral of u to the power -2 is u to the power -1 over -1 from 2 to 3. So we have rho into -1 over u from 2 to 3. Right, so we're going to have rho into -1 over 3 minus into -1 over what? 2. Right, so we have rho into -1 over 3 plus 1 over 2. And that will be equal to rho into -1 over 3 plus 1 over 2 is 1 over 6. So our final answer is rho over what? 6. Rho over 6. So that is the final answer to question number 13 from quiz 2, code 1. So our work done is rho over what? 6. Rho over 6. So beautiful, right? So beautiful and interesting. So that is the end of this question number 2. Now, I want to give you some few minutes so that you reflect on this particular solution. I'll be right back with some couple of trial problems with final answer for you to give it a try. Make sure that you go through the processes to give it a try. Okay, so I'll be right back. Okay, so welcome back from the short break. I believe you have been able to go through the question number 2 and really understand it very well. Now, these are the trial problems that I want you to go through the process and get the final answer. I'm going to provide the final answer, of course. So with question number 1, you have to find the work done. All of them, you have to find the work done. Okay? All of them, you have to find the work done. And the first field for question number 1 is yi plus z x j plus zk. And the curve is r of t equals ti plus t squared j plus ln into 1 plus tk. And the range is 0 and 1 inclusive. Trial 2. I hope everybody can say it's right here. So all of them, you are finding the work done. Okay, so with the answers are for trial 1. For trial 1, you are supposed to get an answer to be 2 plus ln 2. 2 plus ln 2. That is for trial 1. For trial 2, you are supposed to get pi on 2 plus half. Pi on 2 plus half. Then trial 3, you are supposed to get 5 on 4 plus ln 2. So that is for the trial 3. So please kindly go through them, the process step by step, and get the final answer. Once you have it, give me thumbs up or comment at the comment section. Okay, so now this is the end of the line integral in a vector field. Now let's move on to the second section where we are going to talk about the surface integral in a vector field. Okay, so I'll be right back with surface integral in a vector field. Okay, we'll be right back. Okay, so welcome back from the short break. I believe you have been able to glance through the trial problems and you got the answers. Okay, so now let's move on to the second section, which is surface integrals of vector fields. Okay, so with this, it's having some kind of link with the line integrals in a vector field. So that is why we are treating all together. Now, with this, I'm not going to explain or give you some intuitive understanding. It's already understood, right? So I just want to give you some alternative name to the surface integral in a vector field, right? So this is also called the flux, right? It is also called the flux or the line integral, the flux integrals, right? So this is also called the integrals. It's also called the flux integrals. The flux integrals. So if you don't see surface integral of a vector field, then it's the same as flux integrals, flux integrals, flux integrals. Okay, so do you know what? We are going to take a question, and that question is going to explain the concept very well. So give me some short break. I'll be back with some detailed problem. Okay, so I'll be right back. All right, so welcome back from the short break. Now, this is the question that we are going to use to understand the concept of surface integrals in a vector field or of a vector field. Okay, so this is question number 17, code 1, and that is the quiz 2. Okay, question number 17 of code 1, question quiz 2. Okay, so this how the problem goes. Given a surface integral f dot n ds, where s is upper half of a surface, upper half of a sphere, x squared plus y squared plus z squared equals 1, with radius centered at the origin, and the vector field is xi plus yj plus zk. If r is the projection of s onto the xy plane, then we want to find n. We want to find n, the unit normal vector to the surface S. We want to find n, the unit normal vector to the surface S. So we are going to carefully analyze this problem so that we can understand it very well. Once we are done, I'll give you trials. Okay. So first of all, we have to know that this particular problem, okay, we have to know that we were given this, right? S squared plus y squared plus z squared equals 1. Okay, that is what we were given as the upper half of a sphere. So solution x squared plus y squared plus z squared equals 1, and that is the upper half of a sphere, right? Now, and it is centered at the origin, centered at the origin. Now, let's say this is step 1. We have our equation, right? Step 2. Step 2. We have to understand the geometry behind this particular problem. Okay? The geometry behind this particular problem. Now, the surface S, okay, the surface S is the upper half from the question, is the upper half of the hemisphere or the sphere, right? Of the hemisphere. And that is Z is greater than or equal to 0. Now, once we know this information, then we can see that do you know that the full sphere is has a radius r, which is equal to 1. That is the full sphere. And this one is talking about what? Half or upper half of the what? Sphere. So it means that we are going to, when we get the normal, right, we will divide through by 2 to get what? The half of it. So remember that, or recall that the full sphere has radius r equals what? 1, right? Has radius r equals 1, and it is centered at the origin. It is centered at the origin. And we are given the vector field as well, which is SI, F is equal to S plus XI plus YJ plus what? ZK. That is the vector field, right? Interesting. I'm trying to break it into pieces so that we really understand the concept. Okay. So this thing, don't forget, full sphere has a radius what? 1, centered at the origin. And we have been given the vector field to be this. Now, we are not solving the full surface integral. We are just solving what? The upper half. Okay, so we have to find the n, which is the normal vector, right? The unit normal vector. But before we can do that, we have to find the what? The normal vector first. Then after we normalize it. Okay, so we know that the general formula for the outward normal vector on a sphere is defined implicitly by f of x, y, and z to be equal to x squared plus y squared plus z squared minus 1. From here, you just bring this here, equate it to what? 0. And that is the normal vector on a sphere. Okay, so once we have that, then the normal vector at any point on the surface will be given by the normal vector of the surface at any point will be given by the gradient, right? Will be given by the normal vector on the surface at any point will be given by you know, the gradients, right? How to find the gradient. So that is the change in f equals first derivative, partial derivative of the function with respect to what? X, comma, partial derivative of the function with respect to what? Y, comma, partial derivative of the function with respect to what? Z. So what we have to do is to differentiate this function as over here. So our gradient will be equal to 2x, comma, 2y, comma 2z. Right. So once we have this, then the gradient we have here becomes what? The normal vector. Okay, this becomes the normal vector. So the normal vector, at any point x, y, z on the surface is n equals x, y, z. The normal vector at any point on the surface is capital N equals what? X, Y, Z. Now, do you know that we need the unit normal vector, right? So we have to find the magnitude of this. So let me clean this part, okay? Because we will need this question. It has a follow-up questions, right? So let me clean this and find the magnitude here. So the magnitude of this will be equal to square root of x squared plus y squared plus z squared. Right. So that is the magnitude of what? This normal vector. Okay, so once we have that, we know that this right here is equal to what? 1 from the question. S squared plus y squared plus z squared is equal to what? 1. So the normal vector becomes what? The magnitude of the normal vector becomes what? Square root of 1. And that is equal to what? 1. Right. So don't forget, if you want to find the unit normal vector, then it is equal to what? The normal vector over what? The magnitude of the normal vector. So the unit normal vector small n is equal to the big N over the magnitude of the big N. And that is equal to this x, y, z over 1. And that is equal to x, y, z. Okay, so our small n is equal to x, y, z, which is equal to xi plus yj plus zk. Great, great, great. So that becomes our unit normal vector to the surface, si plus yj plus zk. Now, I want to give you some few minutes to reflect on this solution. I'll be right back with a follow-up question. So, welcome back from the short break. I believe you have been able to reflect on the solution for the first part. Now, the question says we should find the s, right? We have to find the x. Okay, so how do we find the x? If you want to find the x in a given surface integral, then this is the formula. It is a formula, okay? It is a formula. And we know that x squared plus y squared plus z squared is equal to 1. So this, we are going to use it a lot. So please record that. Now, this right here is a projection onto what? XY plane, as the question says, right? It's a projection onto what? XY plane. Now, if you want to find the x, then the s is given us. But first of all, I want you to remember this. Z is, if something is projected onto XY plane, then it means that Z is equal to what? Z is equal to a J of X and Y. Okay? If something is projected onto XY plane, then it means what? Z is equal to what? G of what? X and Y. G is equal to what? A function of what? X and Y. That is a projection onto what? X, Y plane. So we say that our ds is equal to square root of 1 plus partial derivative of z with respect to what? X all squared plus partial derivative of z with respect to what? The second variable, which is what? Y all squared. So it is a formula, and this is how the formula is being derived. Okay, so we are going to use this to find our dx. So from here, we know what we need. We know what we need from here. We need to find partial dz with respect to s, and also find partial dx, partial dz with respect to what? Y. So from this, we know that it's equal to 1, right? So it means that if we make z squared the subject, we're going to have 1 minus s squared minus what? Y squared. So if you want to find partial derivative of z with respect to what? X, then we're going to have 2z partial dz with respect to what? X equals negative what? 2x. So we need the x, dz over what? Dx. So we're going to have dz over dx to be equal to negative 2x over what? 2z. So this cancels this, and we have what? Negative x over what? Z. So it means that our dz over dx is what? Negative x over what? Z. So easy and pretty interesting, right? So the next thing is to find dz over dy. So from here again, dz over dy will be what? 2z dz over dy equals negative 2y. So we divide here by 2z, divide here by 2z. This takes off this, and you have 2z dz over dy equals, this cancels this, and we have negative y over what? Z. So we've gotten our what? Dz over dx and what? Dz over y. So we just have to do substitution and we are good to go, right? So we are going to do substitution, then we can know our dx. So our dx will be equal to square root of 1 plus dz over dx is negative x over what? Z all squared plus dz over dy is negative y over what? Z all squared, right? So we're going to have our ds to be equal to square root of 1 plus x squared over z squared plus y squared over z squared, right? So we're going to have the x to be equal to 1 plus x squared over what? Z squared plus y squared over z squared, right? You know that when you find the LCM for the argument in the square roots, you're going to have what? The x to be equal to square root of z squared plus s squared plus y squared divided by what? Z squared. And from the question, we know that, I'm cleaning this part, okay? From the question, we know that s squared plus y squared plus z squared is what? 1. So we are going to substitute that here. Okay, so we have the s to be equal to square root of 1 over z squared, right? And that is equal to square root of 1 over square root of z squared. And this is equal to 1 over what? Z. So that means that our ds is equal to what? 1 over z dx dy. right? The z is equal to what? The s is equal to 1 over z, the x, the y. So interesting and so amazing. So this is the value of what? The answer for what? The x. The x is what? 1 over z, the x over the y. So brilliant. So whenever you are asked of this kind of question, so the question can come in a different format. The question can say that projection of x onto what? Yz. Yz. If the question is what? Projection of x onto yz, yz, then means that the other variables will be what? Your x will be depending on what? Yz, right? Your x will be what? Depending on what? Yz. So you're going to have what? X equals what? J of what? Y and z. Okay? X will be depending on what? Y, z. So it is not always that you'll be having projection onto what? XY. You can have projection onto what? YZ. So if you have projection onto YZ, that means what? Your X is depending on what? Y and Z. So you're going to have X equals what? J of what? Y and Z. So in that sense, the S will be equal to what? Square root of 1 plus partial derivative of x with respect to what? Y, all squared, plus partial derivative of x with respect to what? Z, all squared. So this is projection onto what? Y, Z. Projection onto what? Y, Z. So always, what you are projecting onto becomes your what? Independent variable, and what it's left becomes your what? Dependent variable. So take that very take note of that. Okay, take note of that. It's going to help you a lot. Now I want to give you some few minutes to reflect on this particular solution. I'll be right back with another follow-up question. Okay, so I'll be right back. Okay, so welcome back from the short break. Now the follow-up question is on the same question, okay? But the follow-up question is we are to compute f dot n. That is the vector field dot the unit normal vector. Okay, remember that we had the unit normal vector to be what? X, y, and z. And so this question is going to be very easy because we've already found our unit normal vector. So recall that the small n is equal to x, y, and z. And from the question, our big F is also x, y, z. So the work is so easy, right? So our f dot n will be equal to x, y, z dot x, y, z, which is going to give us, this times this will give us yes. So okay. So this times this will give us s squared. This times this will give us y squared, plus this times this will give us z squared. So if nothing at all, we know that f dot n is this. But recall that from the question, we were given that s squared plus y squared plus z squared is what? 1. So recall that from the question, s squared plus y squared plus z squared is equal to what? 1. So all this is now what? 1. So our f dot n is equal to what? 1. So amazing, so amazing. So that is the end of the problem. Beautiful, right? So if you have a question of this nature, just have to follow the steps one by one and you're good to go. Now, I want to give you some few minutes to reflect on that particular solution. I'll be right back with the last part of the question where it says that we should find f dot n ds, integral of that. Okay, so I'll be right back. Okay, so welcome back from the short break. Now, I believe that you have been able to reflect on the previous solutions and you're good with that. So now let's look at the last part of the question. It says that we should evaluate this line integral, this surface integral of f dot n ds, right? So you have to remember that we obtain f dot n and we obtain the s as well. So now we just have to substitute and then do the necessary. So our f dot n is equal to 1 and our ds is equal to what? 1 over z ds dy. Okay, so we are going to substitute this into this. So we have this f dot n ds to be equal to integral of the function, right? 1 dot 1 over z dx dy. Okay, now remember that from the hemisphere or from the sphere, we know that our z is equal to square root of 1 minus s squared minus y squared, right? So we are going to substitute that information in place of what? Z. So we have this 1 over the z now is square root of 1 minus s squared minus what? Z squared dx dy. Okay, so we have to convert to what? The polar coordinate form. So let x equals r cos theta, y equals r sine theta, right? So we are going to use this polar coordinate form to be able to evaluate the integral. Okay, so remember also that the x dy is r dr d theta, right? So the x dy is r dr d theta. Okay, so we are going to use these informations in place of what we have here. Okay, so now I want you to know the range as well before we continue. Know that the angle full sphere is what? 0 to what? 2 pi. Full sphere is what? 0 to 2 pi. Okay, so this will be theta belongs to what? 0 to 2 pi. And also r belongs to what? 0 and 1. Okay, r belongs to what? 0 and 1 because it's a what? A line. Okay, so we are going to substitute these informations in here. I believe this thing is interesting. So we are going to have from this, we are changing this to a double integral where we are going to substitute, replace it with the polar coordinate. So 0 to 1, 0 to 1 of 0 to, let's begin with the dy, which is the theta, right? So 0 to 2 pi, then 0 to 1 of 1 over this thing here is what? 1 minus r squared. So you know that all this is what? R squared. So square root of 1 minus what? R squared. And the x dy is what? R the theta. So we have r the theta. Okay. So now the work is on integration, right? So we are going to use substitution to do this. But then we have to deal with the inner integral first. Then when we are done, we use that result to evaluate the outer integral. So now I can clean the question because this is the last part of the question. So let me clean this. Let me clean this. So we are going to handle the inner integral. So with the inner integral, we have from 0 to 1 of 1 over 1 minus r squared, that is square root of that, r the theta. Okay, so let's use substitution to do this. So we are saying that u should be equal to what? 1 minus what? R squared. So it means that du is equal to what? Negative 2r dr. Right? Now we have been able to do this. But I love to do change of limits. Right? So let's do that change of limits here. So it means that if r happens to be 0, then u be what? 1. And if r happens to be 1, then it means that u be what? 0. Okay, so let's do the substitution. So we are using change of limit. Okay, so we are going to have now 0 tends to 1, and then 1 tends to what? 0 of 1 over this right here is what? U. So square root of what? U. And then we have to, okay, this is not there. So the r, we have to make the r the subject. So the r is equal to what? Du over what? Negative 2r. Right? So we're going to substitute du over negative 2r in place of what? The r. So times du over what? 2r. That is negative. Okay. So remember there is an r there. So times r. So this takes off this, and then we have from 1 to 0, 1 over square root of u times negative du over 2. So let's factor the negative half out. So we have negative half from 1 to 0, 1 over square root of u du. Okay, so we are going to have negative half from 1 to 0, 1 over square root of u du. So let's change this to have negative half from 1 to 0, u to the power negative half du. Okay, so now we can integrate. So integrate u to the power negative half, and you have what? U to the power half over what? Half from 1 to 0. Okay, and this is equal to negative half into 2u to the power half from 1 to 0. Okay, so we're going to have negative half into 2 times. So we can factor the 2 out, right? So we have negative 2 times half into u to the power half from 1 to 0. Okay, so we see that when you evaluate this, you're going to have negative 1 into u to the power half. We are substituting 0. So we have 0 to the power half minus u is 1, so minus what? U to the power what? 1 to the power what? Half. Okay, so I don't want to clean this because we are going to use this to evaluate the outer integral. So let me write here. Let me manage it and write it here. So we have negative 1 into 0 minus 1. And this is what? Positive 1, because we are going to have negative 1 into what? Negative 1, which is what? Positive 1. So the inner integral gives us positive 1. So we are going to substitute 1 in place of all this. Okay, so let me clean this here. So we are going to have from 0 to 2 pi of the inner integral now is 1. So 1 the theta. Beautiful. So you're going to have integral of 1 with respect to theta is theta from 0 to what? 2 pi. Okay, now let's substitute the limit. When you substitute 2 pi, you're going to have 2 pi minus what? 0. And this is equal to what? 2 pi. So amazing. So you have been able to get our answer for integral r f dot n dx, and that is what? 2 pi. That is 2 pi. So we have 2 pi as our answer to the last part of the problem. So this problem has been able to help us to what? To solve the questions from code 1, quiz 2, question number 17, question number 18, question number 19, and question number 20. Wow, that is so amazing. So please, for this one, I'm not going to give you any trial. Watch over it and reflect on the solutions, and please try to understand it very well for me. I believe you can do it. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye bye.